Okay, great. Just a moment. So thank you, Sangwoo, for the nice introduction, and thanks to the organizers for organizing this nice workshop. Fatma, I missed your talk, but I read the papers. I think it's very exciting. This talk here is going to be less about online tracking and more offline. I'm going to try to talk about the near future of point tracking. So maybe with Fatma's talk already done, I don't need to define point tracking, but I'll do it anyway. The problem to me is this. So given a video and any pixel coordinate on any frame, we want to track the corresponding world surface point for as long as possible. So this is an early visualization I made to show how that works, and so how it looks when it succeeds. And it's useful, I think, to recognize that this problem was made concrete all the way back in 2006. So Sand and Teller wrote in their particle video paper, we want to track the trajectory of each pixel through a given video. Ideally, each trajectory would correspond to the motion of a physical real-world surface point. So this hasn't changed. What has changed is that people have started to care more about the problem and actually work on it. So we've created benchmarks, we've driven up accuracy on these benchmarks, and we've done so with pretty substantial gains. So I've had a few people come up to me over the past couple of years and say that accuracy is saturating on this benchmark or that benchmark. And sometimes I've felt like that too, but it's not really what we're seeing in this plot. So if we take the current set of models and average their results across a wide variety of data sets, you do see that accuracy is reliably going up. And this is real progress. And I'm going to show in this talk that there is still quite a bit of room to improve. And this is all good news, I think, because I believe that point tracking is the ultimate test for pixel-level vision foundation models. So if we can track points in the world over long time horizons without putting a huge burden on our sensor setup, then we can track anything. And this kind of tracking can serve as the basis for not only dynamic 3D scene understanding, but fine-grained understanding of what is happening moment to moment in the world in real life. And I like to remind people that the impact of good point tracking extends well beyond the set of tasks that we normally think about as computer vision scientists. So methods that can precisely measure the movement of arbitrary points in the world have tremendous value in the natural sciences. This is to say that point tracking is not the sort of task where 10 years from now we realize that we never needed it and we're just entertaining ourselves with progress on made-up benchmarks. There are, in fact, real-world use cases to this specific task, even in isolation. It does also plug into bigger systems, which is why we're seeing robotics papers pick up point tracking as a module. So point tracking delivers a foundation for policy learning, because it's very important to perceive how things move and how visual entities correspond across time during an interaction. And this information generalizes better than, say, dyno features or clip features that you extract frame by frame and try to use to summarize the video. I recently joined Meta, where point tracking is already being heavily relied upon for SLAM methods. So point tracks combined with geometry and multi-sensor fusion allow you to build geometric representations of incredible quality. As part of Project Aria, we're now trying to figure out the dynamic part of the scene. So we have data from multiple sensors, and we want to put it all into a common frame of reference. So this involves temporal alignment, geometric correspondence, and eventually tracking everything that moves. So doing this task well has huge implications for assistive AI. So today, I want to show you some ideas, some lessons, and some opinions on point tracking, and also the related problems to point tracking. So the top headline I have here is that point trackers will be dense, fast, and data-driven. And you'll see all three of those points in this first section of the talk, where I'll present a new point tracker we've made called AllTracker. So that section will be the longest, and then I'll move to semantics and some thoughts about 3D. So this this is a paper I don't think that you've read because it only went on archive a couple days ago. And I'm happy to talk about it because this was a very difficult project. But the key ideas, I think, are going to look obvious in retrospect. So this is a point tracker that's, first of all, more accurate than everything else. Second best here is co-tracker 3, which is actually a concurrent work, so it's kind of lucky that we beat it. It's quite memory efficient, and actually it had to be, because I did this before I joined Meta, and I had these particular resource constraints. I could train on 8 A100 40 gig GPUs, and I wanted to test on one of them. In a test time, we can use a resolution of 768 by 1024, still within the 40 gigs. So for comparison, a lot of people in point tracking are working at either 256 by 256 or 384 by 512. So in pixel area, this is quadruple the size of the previous high resolution. So I'll show you the output next. This is already on my opening slide, so you have an idea of it. So for a video like this, I'm laying down a colored grid and I assign a unique color to every grid point. And then I push those grid points along the estimated tracks. And also you can notice it's a little subtle, but when there's an occlusion, then the grid point is hollow instead of filled in. So I think this is a good way to get a sense of the accuracy. And also you can sort of see the pseudo 3D representation that emerges here because it's aware of occlusions. But what's really unique about our approach is that to show this, I'm actually subsampling in our output. So you can subsample more finely to get this. This is at a rate of every 4th pixel. Here it is at a stride of 2. And finally, here's our actual output, which is a unique track for every pixel in the video. So I find this is not really the best way to see the accuracy of the tracking, but it illustrates the density of our output, which is 100%. So this particular video is 576 by 1024, so that makes about 600,000 tracks. And we produce this at about 10 frames a second. So I ran these numbers just last week on an RTX A6000. The main thing that affects runtime is the resolution of the input video. So at lower resolutions, it speeds up quite a lot. We've also hacked out an online variant at the last minute, which is less accurate, but about twice as fast. So this one can take streaming video as input, but we didn't really do any work trying to get the fastest possible model or to try to think carefully about how to do online tracking. We just did the main thing, and then this is what turned out at the end. Although the method is slower at high resolutions, the payoff is that it's noticeably more accurate. So here I've added the higher resolution versions of our model into the plot, and you can see that we push farther away from the current state of the art. So I said higher resolution versions, but really it's the same model. We evaluate one model across all of our experiments, and it just performs better when you give it a higher resolution input. Maybe I'll correct that a little bit to say, it's not that we only evaluate one model in the paper, we have multiple variants, but this like main all tracker model is one checkpoint, and we evaluate that at multiple resolutions. So part of what's interesting here is that most of the baselines actually run out of memory when you try to do this. So you just can't actually give them video that's this large. For some of them, you can, if you get a big enough GPU, like a 96 gigabyte GPU, you could run co-tracker 3. But actually co-tracker 3 plateaus in its accuracy. It doesn't actually get better as you increase the resolution. So this is something also kind of unique about our approach. The key idea in our method is to reconnect point tracking to optical flow. So we're definitely not the first people to make this connection. It was explicit even in the original particle video paper where they used a flow model to get frame by frame flows, and they built up from that. and it's also been explored recently by other smart people. So what I'd like to do now is carefully step through the connections between point tracking and flow, and I want to try to show you how we arrived at the ideas of the full paper. So as a working example, I have this monkey video, and I've unpacked the frames into a row. I'm going to reuse this as a kind of visual motif as we go through. So optical flow is going to start with frames 0 and 1, treating frame 0 as the source and frame 1 as the target. And it's going to estimate flow for that pair of frames. And then it's going to move on to the next pair, and the next pair, and so on. So you do that for all pairs with today's best optical flow algorithm, and you get something like this. So the colors here indicate the magnitude and direction of the motion. And for people that understand the color mapping here, you can take a moment and be kind of impressed at how good this is. So this is from CVPR. I think it was a best paper candidate at maybe ECCV last year. I think it's very good. So that's very nice, but now the challenge is to get long-term correspondences where S and T are arbitrarily far apart. So the basic technique in use since at least 2008 is flow chaining. So the idea here is for a track that is in some XY coordinate, you look up the flow there, which is a little arrow. So it's a dx dy. You apply that to your coordinate, and then you move on to the next frame. So you're retaining a little xy that you remember, and you keep applying a dx dy, keep adding little deltas to your track, and you eventually arrive at a trajectory. So I recently figured out you can visualize that as a dense flow field. So this is new to me. I only figured this out this year, and I think it's pretty interesting to stare at. So this is the flow that you get from accumulating with the technique that I just showed. And you can see that, or I mean, maybe you can't, but that flow field doesn't really represent the long-term motion of the pixels on the monkey. It's something else. It gets a little crazy. So the issue there, which was already pretty well known, by the way, is that when a point gets occluded, there's really nothing good to index in the flow map because flow only describes what's currently visible. So this is why flow chain doesn't work. So as soon as that flow delta lands you on some off-target scene entity, then you start following that target instead of your real one. Another approach is something called long-term flow. So here we keep our source index at the front, and we move the target index forward. So here's what that looks like, again, with CVPR. So in this case, you can see we often now lose the shape of the monkey in our flow field. Sometimes it'll come back. So it's not like drift is accumulating like it was for the flow chaining approach. The overall problem is more like when you have a very large change between the source frame and the target frame, it's just really hard to estimate the correspondences. So in general, optical flow tends to work well when the point you're tracking is textured enough, the spatial support for it is wide enough, the displacement between where you started and where it is small enough, and also there hopefully is no occlusion. So if all this is true, then flow is pretty safe, but the problem arises when it's not true. But anyway, based on those observations, a nice idea here is to get a graph of correspondences at various distances, and then try to find a way to hop along the graph. So for this idea, you can also dig up old references, but Yuri Matas's group has done a nice exploration of it recently. So this basically works, but it's a little slow because you first have to pre-compute all of your whole graph of flows, and then you need to find a way to sort of find a safe path through, and that's usually an optimization scheme. And unfortunately, if you compare the current state of the art, then the accuracy isn't really there. So I think the main thing missing here is the idea of taking multiple frames at a time and estimating their motion jointly, or estimating the multi-frame motion jointly. So that's what we introduced in this paper, PIPS. But what complicates this picture is that it introduces a game of space-time trade-offs. So you can have a narrow temporal window and do dense tracking, or you can have a wide window and do sparse tracking. You have to pick one or the other, because you just don't have enough memory on your GPU to do everything that you want. So this is maybe obvious. And when we commit to the wide window and commit to sparsity, you bring along a few implementation complexities when it comes to message passing between the particles. So in the first paper, I said, let's just keep it simple. We'll make all the particles independent. And then the co-tracker papers introduced attentions between the particles. And eventually they did that with a kind of approximated attention in the style of perceiver IO. And co-tracker 3, the current state of the art whilst we were doing this, doesn't change this. So it's still this kind of approximated attention using these virtual points, virtual tokens. So now here comes the key step intellectually. So to get the all-tracker method in the context of prior work, you have to actually re-examine this space-time trade-off because it's not quite right. So before I tell you more, I'm going to sip my coffee and you can sort of think about this because it looks pretty looks like pretty straightforward logic. And like when I showed it 2 slides ago, you might have nodded your head, but it relies on some assumptions that fall away when you look more closely. Also, if anybody wants, you can raise your hand, tell me what you think here. So first, the density of the output doesn't have such a close relationship to memory consumption as you might think. So modern optical flow methods have really good tricks for efficient, dense inference. They generally do all of their computation at a stride of 8, and then they upsample the output to full resolution with a very cheap operation called the pixel shuffle. So density, full density shouldn't be that much more expensive than, say, a sparse method that's tracking every 8th pixel. And current approaches are actually often tracking every 8th pixel. Second, by wide temporal window, for the current state of the art of point tracking, we generally need something around 16 frames for the window. And then we do long-term tracking by sliding that window around. So it's not that wide, really. And in optical flow, people sometimes, they literally use a batch size of 16. So the memory is there for what we want. So with this information clarified, you realize it's technically possible to have a 16 frame window and dense output. So even without implementing anything, just by reading enough and thinking enough, it's possible to arrive here. So in other words, I used to think that there was a computational barrier, but maybe there never was. Maybe even for PIPs, it could have been a dense method to begin with. So with that idea in mind, we can use an optical flow architecture and sort of reattack point tracking with the new memory that we discovered. So we can come back to long-term flow now. And I mentioned that these flows are bad because the displacements are often too large for the model to figure out. But if we can fix this problem, we'd actually have point tracking because long-term flow is equivalent to point tracking. And there's something very special in long-term flow, which we have so far failed to take advantage of, which is that the output is pixel aligned. So you can pick any pixel in the video on the right, and you can see that there's an obvious relationship across the time axis for that pixel. And this is obviously not true for traditional optical flow shown on the left, and it's also not true for regular video. But in long-term flow, we can take advantage of this fact. So what we do in AllTracker is set up an architecture similar to the state-of-the-art for optical flow, involving dense 4D correlations and iterative refinement, clever upsampling, everything good from flow, plus pixel-aligned temporal attention inside the latent space. So this lets the model propagate information across the time axis while it's solving multiple flow problems at once, and estimate the whole window of flow maps jointly. So in practice, the window size is 16. And this lets us estimate a time-aware flow field, which generally doesn't collapse. The temporal coherence at each pixel is so useful that it disambiguates the correspondences that failed before. So our point tracking output comes from just adding a mesh grid to those flows and then switching the visualization function. So this is again to say that long-term flow is point tracking. So this dense design allows us to have a surprisingly simple implementation. So all of the spatial message passing is achieved with convolutions. All the temporal message passing is achieved with the within pixel attention that I described. And this setup also makes the training pretty fast because it's usually the attention operations that slow down training. And that's especially the case when the attention space is large. But here, the attention is playing a pretty small role. And we don't need a lot of resources to make this work. So evaluating now on the point tracking benchmarks, it's just a matter of sampling some sparse coordinates in our trajectory maps. Part of what's nice here, by the way, is that the model doesn't know what you're going to evaluate it on. So it's tracking everything all the time, no matter what. And that makes the evaluation unbiased, which is not trivially true for many existing point trackers. Another bonus is that since we've now merged the problem with optical flow, we can also add all of the optical flow data sets into our training pipeline. And a little secret here is we're probably still underfitting on the massive amount of data that we've unlocked here. You might also like to know that we output visibility maps and confidence maps, which let you terminate a track or ignore the tracking output during an occlusion or during uncertainty. So these dense outputs are, I think, a little unintuitive at first, but if you stare at them long enough, they make sense. So the key to keep in mind here is that the outputs are always pixel aligned, and they're aligned specifically to the first frame or the query frame. The plot I showed you at the beginning is the result of a pretty thorough evaluation across 9 data sets. We don't get the bold number in every data set, but we win on average. So the average is what I'm showing you in that plot. And the gap widens, as I said, at higher resolutions. And plus, our method is the only one that can deliver dense output at high resolution. So I think this is a clear step forward. So the paper's on archive. The demo is on GitHub. And I'm going to put the training code up next week after I clean it a little more. And that's all tracker. I think you'll agree that that is dense, fast, and data-driven, as the title promised. So let's talk about where semantics fit in here. So if you saw me give talks last year, you might have seen me mention this tag project, tracking at any granularity. Oh, is there a question? Okay, the question is, how does all tracker solve the occlusion problem? So the key is really the size of the window. So since the window size is 16, then any occlusion that's less than 16 frames, it's probably going to be okay because the model can see before and after the occlusion and sort of interpolate inside to estimate what the track is while it's occluded. Yes, that's right. Yeah, so a good step forward, like if GPUs get bigger, or I mean, what I might do now that I'm at Meta and I have bigger GPUs is just train with a bigger window size. That would be a good move. But also you should keep in mind that the design sort of prevents drift. So you're not going to be drifting from one target to the next target because you keep around the source frame. And that's also something that's kind of unique to this sort of point tracking. Well, I mean, by definition, the source cannot be included. The source is what you're tracking when you start tracking. At least, sorry, that's just the way I'm using the word source. Okay, so now for some semantics. So the idea of this tag project was to build a foundation model of motion. So that means to be able to track all kinds of things with a single model, whether it's a limb on an insect or a cell under a microscope. The system should just work. It should be a reliable tracker. So the results you can see here are in fact results from the model we trained. Estimates are in pink boxes and ground truth is in green boxes. And you can see it's doing fairly well. The overall effort here was inspired partly by the segment anything model from last year, or sorry, from the year before. So we wanted to accomplish this same sort of quality and reliability for tracking. And of course, this is also before SAM2 came out. So part of our story was that point tracking has some flaws, even in its definition. So it breaks down when the point that you're tracking comes closer to camera and becomes a whole region. And the same thing, by the way, happens for objects. So if an object starts close up to you and eventually it recedes into the distance, it does become a point. And so it's not great to assume that there are hard lines between points and objects. The goal should really be to track any region of interest and to be ready for the fact that these regions can deform into arbitrary shapes. A second thing we were trying to accomplish in that project is that we wanted to remove information bottlenecks in the architecture. So in any point tracker, including all tracker, we use correlation as a crucial information bottleneck that allows us to generalize. So what I mean there is that when we're tracking a point on the horse, then at some point we compute a correlation map for the entire frame, telling us like roughly what looks most like that point that we started with. So this is a good trick, but it's also holding us back. Because if we only ever see correlations, then we can never learn the relationships between the motion, the objects, and the scene. So in this video, the motion of the horse is partly determined by the rider and the fence, right? And so if you're not looking at that and you're only looking, like you're zoomed so far in on the horse through this correlation filter, you just cannot access that information. So letting the model finally access that broader context opens the door to overfitting, which is scary. And I'll show you later that it is actually a serious problem, but we need to open that door at some point. Overall, we want tracking to get to the level of GPT-4, where it seems to reliably know facts about the world. And this is a non-trivial thing to accomplish. So to do the equivalent for that, for tracking, equivalent of that for tracking, we're going to need a lot of data with tracking annotations. So with the help of a big team, we try to gather every tracking data set that exists. So doing this and properly organizing the data is many, many months of work. So I think we eventually got to about 85 data sets, which turned into about 4 million unique tracking samples with annotations. And that's all just like, that's if you're scraping the internet for anything that has an annotation marking a point, a box, or a mask. But once you do that work, you can try training a giant generic video transformer model, where it just takes a video as input and a prompt indicating what you're trying to track, and it produces tracking as output. So no bottlenecks. The model can use whatever it wants inside those 300 million parameters. It can do whatever strategy it thinks is best to accomplish the task and reduce the loss. And you can just find out at the end what it learns. So here's what that looks like in a little bit more detail. we take as input a big volume of pixels, height by width by time. We compress that down to manageable size with a convolutional network. We reshape that downsampled output into a sequence of tokens. And then we have a high capacity transformer model, do iterated self-attention between those tokens. And finally, we upsample quickly back into a volume. So we're taking as input a volume of pixels and producing as output a volume of masks. And the reason that we deal with these volumes is that we want to learn things about space-time. We want to learn signals that situate moving objects in their scenes, which prior work has missed. And again, an easily measurable benefit here would be to track better through occlusions, because you're able to now see the occluder and sort of understand what is happening. And so I can also maybe add here, although we didn't publish on it, the 3D CNN is a bit of a weakness. If I were to redo this, it would be 2D CNNs. Because those 3D convolutional kernels aren't really good at compressing space-time, at least within our resource constraints. So it's better to have 2D convolutions, and then if you want to do the space-time stuff, it's cheaper in the end to do that with your transformer. So the content of those space-time output volumes looks like this. So first, maybe on the input side, we have an RGB video, and we have a prompt that relates to one specific frame, and that indicates what we're supposed to track. And on the output side, we have 5 channels. The first channel estimates a heat map of where the object's center is. Second and third channels deliver segmentation. And the fourth and fifth channels give us heat maps of where the target's corners are. So these outputs can be trivially post-processed to deliver tracking outputs at multiple granularities. So if you just want point tracks, you can use the center heat map. If you want boxes, you take argmaxes of the top left and bottom right channels, and so on. So this multi-channel output also allows us to connect our model to our huge amount of data sets, which have tracking annotations at different disparate granularities or different types of annotations. This is a way to sort of use annotations of all types. So in our compute setup, it took about a month of continuous training to get convergence. So as you can imagine, experimental errors in this setup are very costly. You make a mistake, you lose a month of progress. But you get through that. Hopefully you didn't have to try too many times. You get through it, the model does eventually okay. So here it is doing mask-based tracking of all kinds of things. And what's nice is like on the right, you can see we're tracking a point in the scene, which is pretty small, using a mask-based method. And this is hard to do. And obviously also we're tracking full objects with masks, more like what SAM does. But so for a project like that, I'm happy to put on a brave face while doing it, but the challenges that came up along the way gave me a lot to learn from. So as I mentioned, long training times were difficult. You need to have a lot of patience for that. We didn't have enough GPUs to do parallel tries. And eventually we ran into very tricky problems with overfitting. So I'm going to try to explain some of those problems here for the first time. And it's going to be a little confusing, I think. So try to bear with me. So to show what overfitting looks like, I want to first show what things look like when all goes well. So we have an input video on the left, and there's a prompt that I'm not showing, but just imagine you click on now the blue cup, and the model produces heat maps across all frames. And these heat maps can be post-processed into tracks shown on the right, but you can already see what's going on through the heat map alone, because it should be putting lots of white area on the target, and it's doing that successfully. And you can see also that we're tracking the robot move that blue cup in and out of the other cup. So it's undergoing a pretty severe occlusion. And it's nice that it works. But now I'm going to break it by running the model at 4 different zoom scales. So you can see already in the 2x zoom scale that something weird is happening. And at 4x zoom, even though we prompted it for the cup, the white area of the heat map is highlighting the table instead of the cup. So apparently the model isn't very good when you zoom in this far. But it turns out the model, the problem, the overfitting problem is subtler than that. It's not just that we overfit to a particular scale. So looking at this 4x zoom alone, we can ask, or we should ask, why would the model ignore the prompt that we're giving it and track the table instead of the cup? So what really is the model paying attention to? And it occurred to me that in all the tracking data sets where we supervise this model, it's very rare to have a cup tracking annotation in a video where the cup is absent for most of the video. So what if the model figured that out? What if it figured out a bias that exists across all tracking data sets and realized that it can just look at the space-time volume of pixels and guess, without even paying much attention to the prompt, what it is it's supposed to be tracking? So we can test that, like see if that's true, by manipulating the video. So here now I have a version on the top where the cup is taken away and another version where the cup stays put. And the prompts and the starting frame are the same in both of these videos. And sure enough, if the cup stays there, the model infers it's supposed to be tracking the cup. Well, if the cup leaves, it decides, oh, I'm supposed to be tracking the table. So you might also ask, is it really about presence or absence? Maybe it's more about motion. Like, is it good at, is it figuring out static or dynamic? So we can create another case where the cup is moving, but we follow it with our camera. And we're showing that now on the bottom. Sorry, those videos aren't synced. Let me do it again. So here now, again, the model tracks the cup. So it does really seem to be about presence absence and not static dynamic sensitivity. And this is a very annoying kind of overfitting. And I don't really know what to do about it because it reflects a bias that's it's in all of the tracking data sets. So if you want to supervise a model with tracking data sets and you want to allow it to figure out any strategy, it's very hard to prevent it from figuring out that strategy. Some more challenges to point out. There's obviously a huge logistical effort in getting a data set of the scale that we did. And inside of that, many of the data sets turn out bad. So people make and release bad data sets every year. And this is wasting our time. In terms of the model, it was also a weakness to focus on tracking a single target at a time. So computationally, it made sense, but our reviewers, where we submitted the paper, were very upset about this. And finally, SAM2 appeared, and mask-based tracking suddenly became a lot less interesting because SAM2 does a pretty good job. So all those factors led into refocusing on point tracking, refocusing on good engineering and rapid experiments, and that's how AllTracker started. So semantics and open-ended knowledge discovery, it's certainly not a dead end, but it's really difficult to explore, especially if you have a limited compute and limited data. So I was actually very glad to see in the workshop website and in the abstract some discussion about low resource settings, because it really does change the research that you can successfully do. But I don't want to convey that that project was a mistake, because a lot of what I learned there applied well to AllTracker, and it's applying well also to the projects I'm currently pursuing at Meta. But anyway, instead of redoing tag right now, my focus is shifting more toward capturing and leveraging 3D information. So we're building 3D point trackers right now, and I have one to share so far called TAPIP 3D. And I'm only going to talk about this briefly to give you the rough idea. This is a 3D point tracker operating in a kind of 2.5D space. So if you have RGBD data, or if you can estimate depth reliably, TAPIP 3D here can give you very good tracking, better than Spatial Tracker or Delta. And the more accurate the depth, the better it does. Method-wise, one quick takeaway I can give is that it pays off to use 3D point cloud-based operations, like finding a point's k-nearest neighbors using 3D distances. And then you can use neighbors of neighbors to propagate information across the scene. So previous 3D trackers define their operations either in image space or on triplanes without going to full 3D as we have done. And we show that this makes a big difference. At Meta, I'm trying to build real-world general purpose 3D tracking so that we can track anything at all at point level accuracy in 3D. And a lot of the effort there really comes down to creating good data sets and also creating good evaluations. So inventing new methods is really easy compared to creating good data sets. And in that effort, I'm hoping to gradually generalize away from single camera data toward multi-sensor setups. So it seems to be getting easier in hardware to have multiple synchronized cameras with reliable calibration and reliable poses. So I'm part of the ARIA team. They make these very fancy glasses now with 7 cameras and IMUs and microphones and so on. So taking the task seriously and even staying within computer vision and saying, I just want to explain what's happening in that RGB camera, it seems reasonable to incorporate information from all these additional data sources. So that's the main content I wanted to show you. I have one bonus slide for students in the room trying to figure out their masters and their PhDs. So if you ask me in general, what makes pixel level vision foundation models work, it's the really boring stuff that you have to pay attention to. So you need good data loaders, you need a clean data curation process, you have to very carefully debug your code, debug your ideas. You need to evaluate in a way that you're not fooling the people around you or fooling yourself. And you need to get good at engineering. So take notice of the fact that every top company does coding interviews. They're not doing that for fun. Good code pays off. So that's all from me. Thank you.
Thank you for the great talk, and we may get a few questions from the audience. Oh, yeah.
So I think we have the first step. I feel like a lot of the models that we have worked on are not really like real actually like the that has a large language model. So purposely like maybe a year ago, it prompts like VLMs like can do whatever to do like visual so level architecture it's really fails, right? But now it's like this one thing that how can that's not to take off. I feel like the accuracy gap is really goes focusing. And the single arch like the issues and components are still accurate. But do you think that the LLM that we are actually see benefit closer to that with the other like more years the revisions of models?
Good question. I'm skeptical. So part of what I worry about is, like I showed at the beginning, these sciencey applications, and what's unique here is, you don't really find this data just on the internet. Sometimes you have to find an actual entomologist, and he'll send you some weird video, and it's something you're never going to see on YouTube. It's never going to enter into the training of these large VLMs. I'm not sure they're going to be ready for this sort of tracking. Like if I tell it, track the legs of that grasshopper, I'm not so hopeful. Whereas a model that's focused entirely on just low-level vision, understanding maybe the structure, understanding 3D a little bit, and has trained his whole life to track anything, whatever it is, and that's his only job, that seems more hopeful. I also showed at the beginning this sort of output. You can hope again that a VLM is going to be able to take that video, take maybe an hour of you walking through a city and figure out some internal representation that's of that quality. I don't think it's going to happen anytime soon. So to get here, you need to master low-level vision, it needed to incorporate geometry. And I don't think that those are strengths of current large VLMs. Yes, that's a great distinction. Yeah, if you want reasoning, then yeah, VLMs are great, and that would be actually a great research topic, like trying to merge that with the low level accurate vision, because we don't really have good methods for bridging that gap.
And other questions? Oh, actually, I have one question related to the previous question. So when you worked on all tracker, did you consider to put some memory module to avoid such a occlusion beyond 16 frames?
No, I don't think I spent much time thinking about that.
Yeah.
There is technically something you might call a memory, where we keep around the initial frame and all the features of that frame. And the model actually has multiple copies of that it tries to use while it's inferring the motion that corresponds that frame to the other frames. If not propagating the updates to that memory across windows, because that update operation is kind of risky, right? Like if you make a bad update, then you forget what you were tracking in the first place. And like in practice, it turned out we don't need it so much. So we just left that aside.
Okay. So, but for your future project, are you considering to put this, or you think the memory is unnecessary?
I'll have to think about that. I'm not convinced that it's necessary, but it's also not a thing I'm very confident about. Like I'm happy to be wrong.
Great. Thank you so much.